we've been looking at the hyperbola where the focus is on the x and y axes. But of course, prior to this year, we're used to seeing the hyperbola like our regular hyperbola, y equals 1 on x. How do we get that equation? I mean, where does it come from? So we're going to look at what we call the rectangular hyperbola, which is basically any hyperbola whose asymptotes are perpendicular to each other. So the classic one we're used to seeing, of course, the asymptotes of the x and the y axis. So of course, yes, they're perpendicular to each other. All right, well, we know the equation of our asymptotes. Let's go back to our standard one we've been dealing with at the moment. And it's b on a is the slope of one of the asymptotes, minus b on a is the slope of the other asymptote. We're saying that they're perpendicular to each other, so they're going to multiply together to give -1. Well, if that's the case, b squared must equal a squared, so b is a. So we could rewrite the equation now to be x squared minus y squared is equal to a squared. So it's probably the closest to, whereas the circle is the ellipse that's perfect, if you like. I suppose we could think of the rectangular hyperbola to be the perfect hyperbola. Same sort of deal. X squared minus y squared is, well, for want of a better word, the radius squared. So eccentricity will no longer be a squared plus b squared on a squared. It'll be a squared plus a squared on a squared, which is 2. So root 2. The eccentricity of every rectangular hyperbola is the square root of 2. So don't waste time. I've seen it, the question asked several different ways. Sometimes it's multiple choice. Sometimes you actually have to work out in the question. And of course, you just write it down if you know it's a rectangular hyperbola. Don't waste time deriving it. Rectangular hyperbola. Eccentricity is the square root of 2. All right, so as I say, how on earth do we get the hyperbola that we were used to seeing, y equals 1 on x? There it is when the foci is on the axis. So basically what I want to do, because these asymptotes now, if a is equal to b, are y equals x and y equals minus x, which we know are at 45 degrees at the moment. So basically I want to rotate this shape 45 degrees. If I do that, then the asymptotes will become the x and the y axes. So I've actually labelled them, you'll notice, capital X and capital Y, so I don't get confused. This is where we're going to bring complex numbers into it. So I'm now going to think of it like the Argand diagram. So P, yes, it's a point on that hyperbola, but I'm going to call it the point x plus iy, the complex number x plus iy, and I'm going to rotate 45 degrees. Well, if you remember back to complex numbers, rotation was multiplication by another complex number. Now, I don't want to change the modulus. I want p to be the same distance to the origin, but the angle is 45, so we'll multiply it by cis 45. Okay, let's see what happens. So if I get x plus iy, I'm going to multiply it by cis. We'll expand that out to what we know to be cos 45 plus I sine 45. And of course, they're both 1 on the square root of 2. If I expand the whole thing out, eventually, and breaking into its real and imaginary, okay, because the real will be the new point, the new x value, the imaginary will be the old y value. So when x and y, capital X, try it again. When capital X and capital Y are the axes, the coordinate of capital X will be little x minus y on root 2. And the coordinate of capital Y will be little x plus y on root 2. Well, if I multiply them together, then I get little x squared minus little y squared over 2. But hang on, that was the equation of the rectangular hyperbola when it was in the position where the foci were on the axes. And we know that x squared minus y squared was equal to a squared. And so there we get it. X times y is equal to a constant number, okay, which is our classic rectangular hyperbola. Do not fear, you don't have to do that each time. Still, it's nice to know where it comes from. You never know, they might. Well, let's work out where the focus has been moved to. So the focus was AE0. So root 2, because remember we said the eccentricity of every rectangular hyperbola, was the square root of 2. We're going to multiply that by cis 45. And we end up with A plus AI, which is really cool, because it just means that the foci has moved to AA. It's on the line y equals x. Well, that makes sense, because remember, we've rotated everything 45 degrees. So if it was on the x-axis, rotate 45 degrees, it should be on the line y equals x. So it makes sense. And it's kind of nice that it turns out to be A. The other foci, of course, then would be minus A, minus A. The directrix, a little bit more work involved to work this one out. It was the line x equals plus or minus A on E. So again, we know the eccentricity is the square root of 2. Okay. Our directrices, before we rotate, are parallel to the y-axis. If I rotate 45 degrees anti-clockwise, they'll go parallel to y equals negative x. So I know the slope of the directrix when we rotate it is negative 1. Therefore, it must have the equation x plus y plus some constant number is equal to 0. We just got to work out what that constant number is. We know the distance between the two directrices will be 2a on root 2, because each one was a on root 2. Now when I rotate it, that distance is not changing. So I know that the distance from the origin to the directrix is a on root 2. Even when I rotate it, it's still a on root 2. Well, I can use the perpendicular distance formula then. And so with that perpendicular distance must be a on root 2. And I'm going from the origin, so the x and the y, they become 0. And I just get the absolute value of k on root 2 is a on root 2. Well, what do you know? K turns out to be plus or minus a as well. So our directrices just become x plus y plus or minus a. I suppose it doesn't matter which side we put it on, because when you move it, you change the sign still. So quite easy to remember. AA for the foci and x plus y equals a for the directrices. To summarise all that then, xy equals a constant, but think of that constant as a half a squared, because we need to know a. Once we know a, we can say straight away, well, the foci plus or minus a plus or minus a. And the directrices x plus y equals plus or minus a. So that's the key to remembering it. Don't think of it as just xy equals a constant. Think of it as xy equals half a squared. Eccentricity is always root 2. Well, the parametrics now, again, I don't think of it as xy equals a constant for the parametrics. I think of it as xy equals a constant squared. The parametrics here are more like the parabola. I'm not going to do it with reference to the auxiliary angle. Okay, I'm just going to do it like this. I'm going to say, well, x could be c times some parameter, and y will be c divided by some parameter. Multiply them together, you get c squared. So when we're talking about parametrics, the constant, think of it as c squared, rather than just a constant, and you get your parametric form quite easily. The tangent turns out to be x plus t squared y is 2ct. The normal will turn out to be t cubed x minus ty equals c outside of t to the power of 4 minus 1. I haven't bothered to derive them here. Trust me, you'll have plenty of opportunity to do that in the exercises. But again, if the reality, if you memorise it, fantastic. If it's just a one marker and they say write down, you can. But you still need to know how to derive it. Just like the differentiate, find the slope, it's find the equation of a line at the end of the day. Chord of contact for this one. What does one think it might become? Let's see. Okay, we'll do it like we did with the parabola last year. We'll go all the way through and see what happens. So rather than doing the quick method where I go, oh look, equation of the tangents this, equation of the tangents that. There's 2 points in parametric form, CP, C on P, CQ, C on Q. We want to show the equation of PQ, it will end up being, so that chord is x plus PQY is C P plus Q. Find the point of intersection of the two tangents. That point of intersection I'll call x0, y0, the external point. the point of intersection ends up being 2cpq on p plus q, 2c on p plus q. But hang on a sec, we said that's the point x naught, y naught. So I know x naught is 2cpq on p plus q, y naught is 2c on p plus q. Remember what we're trying to do? We're trying to eliminate the parameter out of this equation. I don't want pq, I don't want p plus q. Okay, so if I rewrite, which one have I subbed in first for? PQ. PQ I could rewrite as P plus Q. Yes, I haven't got rid of all the P's and Q's yet, but I could rewrite it as P plus Q on 2C if I rearrange the X naught one. Okay, but I still got to get rid of P plus Q. Well, I can use the other one to get rid of the P plus Q. So I've got X plus 2C X naught on 2c y naught y plus 2c squared on y naught. Get rid of the fractions. Bingo, look at what we got. It mimics the equation. Because the equation was xy equals c squared. So therefore, if I go xy plus xy, I would get 2c squared. So you make, in one of them you make y naught, the other one you make x naught. There's your quarter contact. So, just like all the others, it mimics the actual equation itself. It's an old question, but it comes from 1991. We love that because that's a palindrome, and so it's got to be a good question. The hyperbola h is xy equals 4. Sketch h. Now, if there's ever a gift question you're ever given in an extension 2 paper, that's got to be it. You just got to draw xy equals 4 and show where it intersects the axis of symmetry. Oh, okay. The hyperbola, oh look, drawing the axis of symmetry. They said to label where it is. Oh, it's on the line y equals x and x times y equals 4. Just in case, let's work it out. xy equals 4. So, x is plus or minus 2. So it must be 2, 2 and minus 2, minus 2. Show that the tangent. So in this case, I can't just quote it, I've got to derive it. But in case I muck it up or for some reason I can't do it, at least I've got it there I can use in later parts of the question. So okay, differentiate y, I get minus 4 on x squared. Substituting x equals 2t, I've got minus 1 on t squared. For the slope, point slope formula, play around with it. Okay. We've got our equation of the tangent, x plus t squared y is 4t. Now comes the interesting bits. S can't equal 0. S squared can't equal t squared. We have to show that the two tangents, the one at P, the other one at Q, intersect at this lovely point. 4st on S plus T, 4S plus T. Remember the advantage of parametrics? You don't have to rederive everything. You're just changing the parameter. So we've found the equation of the tangent at P to be x plus t squared y equals 4t. Well, Q, the only difference is instead of the parameter being t, the parameter is s. So logically, the equation of the tangent is x plus s squared y is 4s. We want to find the point of intersection, solve them simultaneously. Let's eliminate the x's, the coefficients are already the same. We get t squared minus s squared y. That's the difference of two squares, of course. Now, I can divide everything by t plus s, t minus s, because we are told s squared can't equal t squared. Therefore, s does not equal t, so t minus s, that doesn't equal 0. And s can't equal negative t, so t plus s can't equal 0 either. So it is okay to divide by that. So I end up with y is 4 on s plus t, which is what I'm looking for. Now I've got to substitute back in to get the x value. So x plus t squared times that. So we now have 4t squared on s plus t is equal to 4t. Move it to the other side, bit of algebraic fraction work, but we get our answer of 4st on s plus t. So yes, m is indeed 4st on s plus t, 4s plus t. Well, if you remember from parametrics last year, once we find a lovely point like that, we usually follow it up with a, what is the, Oh, what a surprise. Here we go. Suppose that S equals minus 1 on T. Show that the locus, whatever, of M is a straight line through the origin, but not including the origin. All right, remember we found that X is 4st on S plus T. Y is 4 on S plus T. We've now been given a condition. We don't have to work out the condition to eliminate. S is minus 1 on T. Well, if S is minus 1 on T, another way of saying that is ST is negative 1. All right. Well, that means X is minus 4. Oh, look. X is minus 4 on S plus T. Y is positive 4 S plus T. Could there be a relationship there? In fact, they've even given me a hint telling me it has to be a straight line that goes through the origin. Well, Y is equal to negative X. That would indeed be a straight line that goes through the origin. However, they've put the little kicker in there that it can't include the origin. Why is that? Well, have a look at X and Y. It's a fraction with a constant on the top of the fraction. That fraction can never equal 0. We will never get the point, 0, 0. Okay. So Y equals negative X. However, 4 on S plus T can't equal 0. So therefore, M can never be the point 0, 0. So the locus of M is Y equals negative X, excluding 0, 0. If you think about it logically, the reason it can't go through the origin, you've got two tangents. They're related by one slope is S, or S equals minus 1 on T is the parameter. It's impossible to draw two tangents and meet at the origin, because the origin is where the two asymptotes meet. Now, the syllabus specifically states this. When it comes to locus questions, it will only ever be on the rectangular hyperbola. They will not ask locus questions on the ellipse, on the regular hyperbola. Now, they might still ask questions about geometrical properties, things like that. But when it comes to finding the locus, it's restricted to the rectangular hyperbola.